So thank you very much for the invitation. So today I will speak about another candidate, multilinear maps. This one is over the integers, so it's slightly different from the one Shai presented this morning. So first thing, I wanted to start with a timeline. So multilinear maps are really hype, and there is this curve which is known, which is called the hype cycle. So you have the time in the x-axis and the visibility of the hype thing in the y-axis. So every hype cycle starts with a technology trigger. So for multilinear maps, we can say more or less than, so we had some papers before that only with the theoretical idea, but we had candidate construction 2 years ago in 2013. So this is Eurocrypt and Crypto. So Sanjam, Craig, and Shai presented their construction, and then some papers started using it, and we proposed just a few months later a second candidate construction that I will speak about today. Okay, so that was a technology trigger, and then the second phase of every hype cycle is the peak of inflated expectation. And I will replace with a synonym here, I/O. Well, okay, I'm slightly exaggerating. So the thing is, since we could we have a candidate construction for I/O from multilinear maps, this really gave a lot of interest in that primitive. So this is really something that is worth working on. And then there's a big thing here, and that's the fraud disillusionment. Okay, this is mainly the attacks. So I have a bunch of attacks there. So it's actually started. So from the beginning, we knew that there were a weak discrete log attack on the first candidate scheme. But then the CLT scheme got completely broken. And then 1 week later, there were 2 tentative fixes on the print. And then these fixes were broken again, and the attack was extended. So we were really here, we're really at the bottom here. And 1 week later, then there's a break of graded decisional Diffie-Hellman in GGH. So GGH is also broken in a way. So we're really there, and that was kind of, depressing. But what about today? So today, I'm expecting that we're under the 4th phase, which is the slope of enlightenment. So Shai talked this morning about the graph-induced scheme here that appeared at TCC this year. And now I will focus on the new multilinear maps over the integers. So this is a modification of the of the second candidate construction that essentially is modified deeply to resist to all the attacks. Okay, so let's jump into it. Let's describe what is the initial CLT scheme, and I will actually go over how we made it, how we constructed it in order to understand what we did. Okay, so that's the second candidate construction. And this is kind of nice because it's also a composite order map. So the idea is that you can encode actually vectors. You're encoding, vectors, and you can, when you add them and multiply the encodings, it add and multiply every slot in the vector. So this is nice, and it gives something interesting to build I/O, for example. So we actually followed the GGH13 recipe. So we did some levels using multiplicative mask, and we did zero testing by multiplication and using the shortness. So I will come back to that. And as GGH13 and as actually GGH15, our scheme is also based on homomorphic encryption scheme. But our scheme is based on the on the FHE scheme based on the approximate GCD problem. Okay, so this scheme was actually used in a lot of papers because of the composite order maps, and also because we were it seemed at first that the decisional linear problem and the subgroup membership assumption were hard in this setting, so it was really something interesting here. Okay, so Shai mentioned it this morning. So the current multilinear maps, they're really similar in a way to homomorphic encryption. You want to compute homomorphically over encrypted data, but the difference is at the end, what you want to do with the data. Okay, so instead of encrypting a value A for homomorphic encryption, you encode it. Okay, but that's more or less the same. And in both cases, you want to compute low-degree polynomials in several encodings or several ciphertexts, up to a certain degree. But then, for multilinear maps, what you want at the end is you want to test if it's equal to a certain value, or test if it's equal to 0, because you can always go back to 0, at the last level, and only at the last level. And you want that if you go beyond the last level, you have too much randomness and you don't know what to do. For homomorphic encryption, this is different. You want a really strong semantic security. You can do the operation, but at the end, it's indistinguishable from random. So you don't know what is encrypted. So the difference is essentially here. How can we provide this helper element at level K that is a defective secret key that will allow only to test if it's a 0, if it's an n-value. Okay, so let's start from the homomorphic encryption scheme over the integers. So it started with Van Dyck, Gentry, Alevi, and Vaikutana in 2010, and then it got modified in a series of papers. So the secret key is just a prime, P, and part of the public key, it's actually public modulus here, it's a multiple of the prime times something which is actually really, really, really large. Millions of bit large. But it's hard to factor. Okay, so that's a public modulus. And what is a ciphertext? So a ciphertext is just a near multiple of P. So it's a multiple of P, so it's Q times P, where Q is mod this large factor here, plus your message, and plus your message is mod G, plus G times small noise. Okay, so actually this thing here, GR plus M, is way smaller than P. That's the idea. Okay, so we can rewrite that slightly differently. We can rewrite it as a CRT. What does it mean? It means that mod P, so we add GR plus M, which is this small value here. And on the other, mod Q0, this is actually a random value. And this random value is what enables us to prove the security under the approximate GCD assumption. So to decrypt, you just take mod P, you get this value here, and you take it mod G, and you remove the G times R. Okay, so we can extend it further, and this is as in these papers here. So instead of having only one P, you can have multiple PIs. So now you have multiple PIs in the secret key. Your public key is Q0 times the product of the PIs. And you have several slots here, and on each slot you have your message, so the ith coefficient of your message vector, plus GI, which is the message space for the high slot, times some small noise Ri. Okay, so that's just a way to extend it, and it's actually interesting because, as I said, the random here is actually way larger than the PI. So by batching it this way, you're actually saving space. You're not. It's not. It's interesting to batch it this way. You can batch several elements in a ciphertext which is more or less of the same size as before. Okay. So what happened on each slot? So on the first slot, when you do operation, it's only random values. So the random values will add or multiply, so it will stay random. But on these slots here, so these are small values, right? So when you add to those, this is mod 1 of the slots. So when you add two small values like that, the value is slightly bigger. It increased by like 1-2 bits. But when you do a multiplication, it's like it doubles the size. So it's actually, with multiplication, the noise growth is exponential. So you can do several operations, so multiplication, but then you're stuck because you have a like kind of big noise in your ciphertext or in your encoding, and then you're stuck. You cannot do another operation, otherwise it will overlap mod p, and you will add randomness in the message, and you will lose correctness. Okay, so then you're limited to like a certain number of operations. This is why it's a somewhat homomorphic encryption scheme. Okay, so far so good. So let's apply the GGH recipe. So first thing, we want to add sharp levels. So we want this notion of levels in the multilinear maps. So what they did in GGH and what we did too is add a multiplicative mask. So let's draw a random value, mod x0, so all the encodings are mod x0. And then you encode a vector m at level j by dividing your ciphertext by z to zj, mod x0. So this is nice now, because when you do additions of encodings, you can only add encodings at the same level, because you need to have the same denominator here, and it will yield the encoding of the sum at the same level. And when you multiply an encoding at level j1 and an encoding at level j2, the exponent in the z will add, so you will get an encoding at level j1 plus j2. Okay, so we got these levels, and that sounds interesting. Second thing, we want to test for 0. Okay, so in GGH, they multiply by something and use the shortness of the noise. So let's look at what we really want to do. So we want to test whether two encoding at the level k are equal. So it means equal here means that the vector m and the vector l are equal to the vector 0. M minus l is equal to 0. Okay. So what is an encoding of 0, actually? So if we look at before, so this is the ciphertext, and in each ciphertext you have a plus mi here. So now all the mi is equal to 0. So it seems that if we want to test for 0 and use the shortness, so we have shortness in these slots here. The ri times gi are short. And then we have to cancel this z thing here, and we're quite annoyed by this randomness here. So yes, that's what I was saying. So the idea of GGH is to multiply by an element which will cancel this thing here, and we'll use the fact that these things here are small. Okay, so let's rewrite this thing here differently. So we can rewrite the CRT as a sum. So it's a sum of gi ri times something that is the coefficient that will give the CRT. So here the pi star is the product of the pj, except for j is equal to I. So if you take it mod p, so if you take p2 star mod p1, you get 0, right? So if you take this sum mod p1, you get only the first term, and the first term is what? Is g1 r1 divided by z to zk mod p1. So this is exactly the CRT itself. And then you also have this random thing times the product of the pj. So if you take this mod q0, then this is random, so this is random, so everything is random. And that's how we got to the formula before. Okay, so that's just another way to write it. And we're quite annoyed by this value here, because it's a random value. So there's no really way to exploit the fact that these terms are small, because this value is like really big, really big, and it scrambles everything down. So what we want is actually to work mod the product of the pj. We don't want this term here. It's like really annoying to zero test. So that's actually what we did in the paper. We said, okay, let's take x0 to be the product of the pj. So it means actually we don't have this random slot anymore in our scheme. But this slot was what was helping us to prove, to reduce the thing to approximate GCD. So now we don't have a reduction to approximate GCD anymore. But it seems that if I give you a CRT of many, many values, small values, where like, consider n to be in the order of 10,000 or something like that, and the primes they're all like 2,000 bits, and I give you the CRT of these small values, it seems hard to distinguish it from like any uniform element. Okay, so now if you look at an encoding, so x0 now is the product of the PJ, it's just a CRT of small value divided by z to the j. So this is a level thing, and this is nearly a ciphertext, except that we dropped the first slot. So now what is the zero testing procedure? So we'll multiply by an element pzt. And so what we want is we want to, let's look at it here, so we don't have this term anymore. We want to cancel the divided by z to zk, so we'll have to multiply by z to zk. And we want this to be small in a way. And so we need to cancel this thing here, which is not small. So it means we actually have to multiply by the inverse of this here. And this is of the size x0 divided by pi, and this is way smaller than pi. So it means that if this wasn't here, then it would be way smaller than x0. So you could test it. So that's what we do. We are actually, so this is a pi star and the zk, and we're also multiplying by a really small element hi, which will add randomness for the security. And we also multiply by the inverse of gi. So why? Because now when you take, so this is your encoding of m. So on each slot it's ri, gi plus mi. So when you multiply it by this element here, mod x0, mod the product of the primes, what you get is the hi is staying here, the pi star is staying here, and then you multiply this thing here by this thing here. So the zk is like canceling out, and you have ri plus mi times gi minus 1. So this is nice because when all the mi are equal to 0, then this disappears, so the ri are small, times the hi are small, and the pi are of size h0 divided by pi, so it's way smaller than x0. So everything is way smaller than x0. So you get this equality over z, and it's meant that the absolute value is way smaller than x0. But when m is not the zero vector, then one of these mi times gi minus 1 will be big, because gi minus 1 will be big, mod pi, and then it means that all this sum will be big, and you will have something that is big compared to x0. So we actually have to give several PZTs in order to prove the equivalence in the other way. But
so that's from CLT
13, yes. Okay, so that was more or less the scheme. And what was the hardness assumption on the scheme? So the first one was the graded decisional Diffie-Hellman assumption, which is essentially I give you k plus 1 encodings at level 1, and I want you an encoding at level k, and I want you to guess whether the encoding is a random encoding or if it's a value encodes the product of all the others. So of course, so that's exactly, in a way, the multipartite key exchange protocol. So every one broadcasts, so that's what Shai said this morning, everyone broadcasts a value, so everyone broadcasts an encoding of a random value at level 1. And what is their shared secret? It's actually the product of all the encodings but their own, so it's something at level k, and they actually multiply by their own secret encoding at level 0, so it does not change the level. So they get an encoding of the product at level k, and an adversary does not have the encoding at level 0, so it cannot produce an encoding at level k. It can only produce an encoding at level k plus 1, but it does not even make anything because there is no level k plus 1. So it's hard to distinguish. I mean, the assumption is that it's hard to distinguish. But we don't have any like reduction to approximate GCD or anything like that. And the asymptotic parameters, so we had a heuristic security analysis, so we considered some attacks, like orthogonal lattice attack on encodings, GCD attack on zero testing, attacks on the inverse of the zero testing matrix, Adams-Satsepson attack, brute forces of the noise, and stuff like that. And every one of these attacks was giving a constraint, and then we had the scheme with the constraint. Okay. So we also had the decisional linear assumption and the subgroup membership assumption that were thought to be hard in our scheme. But that's actually not the case. So some Cheon, Han, Lee, Ryu, and Selle came with a bazooka and shot us. So they wrote a really nice paper at Eurocrypt this year, and they describe a probabilistic polynomial time attack against our scheme. And the attack is really, so it means that if you have low-level encoding of 0, then you can recover the PIs. And the PIs were the secret value, you know, in the public modulus. And actually, if you can recover this, then you can break everything down. Okay, so I have to describe what they did in order to explain how we try to protect ourselves against this attack. So if you have to remember something, the thing is they're exploiting the linearity of the zero testing procedure. So actually, what is the zero testing thing? So when you compute this mod x0, you're actually computing an inner product of two secret vectors. So it meant that if you split the first encoding and three values, so this is an encoding of 0 at level k minus 2, so a low-level encoding of 0, a target encoding, and an helper encoding at level 1. If you take this, then you get an inner product of the arrays coming from the encoding of 0 here, and these values are just the values on the slot of these encodings here. So you get, you know, a four-partite inner product, so you can rewrite it this way. This is actually a row vector times a diagonal matrix, where each element of the diagonal matrix is this bi times this element here that comes from the p(z)t times a column vector. And when you see it that way, you're like, okay, let's run it with different encoding zeros and different encoding c in order to extend it to matrices. So if you do it n times, if you have enough encoding of 0, a low-level encoding of 0, and enough helper encodings, then you can construct a matrix, which is a matrix R times a diagonal matrix with these elements, which are really secret values here, times a matrix C. Okay, so we did it once, so let's do it again. That's essentially the attack. So let's take the same encoding 0, the same encoding C, but this time we'll apply it on a different target. So now I will get twice the matrix as before, so a matrix R times a diagonal matrix, so this time the diagonal is different, times a matrix C. So let's invert the second one, and with high probability it will be invertible, because we're actually taking the over all the randomness that will be in the encoding, that will be inversible. And then when we see that, of course, we want to multiply it. And when we multiply it, the C here is canceling out. And here you have two diagonal matrix, so you get like the product of the elements on the diagonal. And now it's like way better, because you get a matrix which is equal to a matrix R times a diagonal matrix with secret values times R minus 1. So what you want to do, obviously, is to compute the eigenvalues from here. Because the eigenvalue of the matrix here is exactly all of this bi over b prime high. Okay, so that's just what I said. So you compute the eigenvalue, and you can compute them. Oh yeah, sorry. So you were actually, before, you were doing the inversion of a Q, right? So you had two integer matrix, so you can invert them over Q, and then you get this, and this is over Q here, and you can compute the eigenvalues, and this will be rational numbers. So you get the eigenvalues, and that's bi over b prime I, but you get like the reduced form of them. But what you do have is if you take, it means that essentially from this equation you have bi times b prime I is equal to b prime beta prime I times bi. So it means that on the ith slot here, if you multiply beta I prime here with this encoding here, and you remove beta I times this encoding here, you will get a 0 on the ith slot. So it means that pi will divide the element that you have here. And now you can just compute the GCD. So you compute the GCD of this value here, because pi is dividing this value, with x0. And x0 is the product of all the pj's, so you can recover pi from it. And with I probability over everything, you recover exactly pi.
How do you get the betas from the ratio?
So you're actually computing the eigenvalue, so it will give you a value like a rational number, and the rational number is... Yes, exactly. That's the numerator and the denominator. So then you recover the pi, and if you have the pi, then everything breaks down. So even worse, so 1 week after this attack, 2 fixes were proposed, but their idea was, okay, these low-level encoding of zeros are annoying. So let's prevent anyone to have low-level encoding of zero. I want you to so it means that at the top level, in order to zero test, you will have to do something differently. You'll have to do a sum. You won't have this multiplication structure anymore. But they were using the zero testing as like a black box, not modifying the zero testing phase, only modifying the form of the encoding. And the thing is, you can actually generalize this attack. If it's a sum, for example, it doesn't matter. You just need bigger matrices. Some other remarks: you don't actually need low-level encoding of zero. What you need is that when you multiply all these a's, which is here, times the target b, which is fixed, times the c, you get an encoding at zero at the top level every time. So when you virize the a's and the c, you still get an encoding of zero. So you need orthogonal encodings in a way. Over remark, you don't actually need the matrix B to be diagonal. It can be diagonal per block. So now it means that the eigenvalues might be in complex numbers, but you can compute the characteristic polynomial and it will cancel out mod one of the slots. So that's different ways to extend the attacks. So it seems really bad, but the thing is there a way to thwart this attack? We really want to remove the linearity from the zero testing. One thing is, the encodings, they look like DGHV ciphertext. They look like the somewhat morphic encryption scheme ciphertext. The only thing is we dropped this random element, which was helping for the reduction to approximate GCD, but in a way, their form should not be a problem. So what we did in the new CLT that will appear at Crypto is to modify the zero testing procedure itself rather than modifying the form of the encodings. So in a nutshell, the idea is we'll not zero test mod x0 anymore. We'll zero test mod a new modulus, a modulus which is completely drawn independently. And the x0, which was useful, so actually we cannot assume it to be public anymore. And it's even better, because if it's not public, it means that it does not rely on the on factorization anymore. So that's kind of nice. And actually, at the end of the attack, we are doing a GCD with x0. So if we don't have x0s, it means the attack can just be more complicated in order to succeed. Anyway, I'll come back to that.
That's the new modulus?
So we do the zero testing mod a new modulus. So we do, essentially we keep the same thing, mod x0 all the way long, but only at the end, at the top level, in order to zero test, we switch to a new modulus. And we do the zero test mod this new modulus here.
Zero is the old modulus.
It's an old modulus. It's a product of all the primes.
So how can you do anything if you don't know what you're...
Yes, I'll come to that. Okay. So what was the idea behind it is that actually there is some inherent randomness in the current encodings. So this is the form of the current encodings, so mod x0. But what it meant is that it's actually equal to a sum of this form here. So the UI here are just in a way to write it down more. I mean, that's a scaling factor for the CRT. So that's a sum of this element times UI plus an element A times x0. So mod x0, you have this is not here, but and you take this mod x0. But if you look at over Z, you have a value A here. And this value does not depend linearly on the Ri, which are here. So there is like this inherent randomness in the encoding. So we want to use this thing. Okay, so this is actually different from the random Q prime that we had before. So remember, before we had like this overslot and we had Q prime times the product of the PJs. But this is not the same here because when all the MR are equal to 0, you have only Ri here. And the Ri is small. And the UI is of the same size as x0. So it means that the size of A is the same size as this term here. So in particular, when you have a 0 vector, the value A here, the random A here will be small. So that's different from before, because before we had something that was completely random here, and that was large, whether the vector M was equal to 0 or not. And now it depends also on the vector M itself. So if the vector M is not 0, then A will be big. And if the vector M is 0, then A will be small. So that's a different setting as before. So we want to exploit this thing here. So how can we do that? So our idea is to switch to a new modulus. So we pick a random large prime, which is larger than x0. And we want to generate a new zero testing parameter so that an encoding of M times the new zero testing parameter mod this new modulus is way smaller than the modulus if and only if the vector M is equal to 0. So in particular, if you rewrite this down, it means that this was the encoding here. If we take this mod x0, so it means that when all the mi are equal to 0, this will be small here. So it means that we would want the ui times alpha zt to be small. And if all the mi are small, this is small too, so we want this here to be small too. So we want to find a vector, an integer alpha zt, so that alpha zt times all the ui is small, and alpha zt times x0 is small, compared to m. So how can we do that? So I give you n, and I give you the ui and the x0, and how do you find a small an integer so that all these values are small? So it's not obvious. I mean, it amounts of finding a short vector in this lattice here. I mean, the lattice spanned by the rows of this matrix. So what you could do is to use LLL. I mean, you can use LLL. You will get a somewhat short vector, and we can actually tolerate an exponential approximation factor of SVP. It doesn't matter. It just means that we'll increase our parameters more. It's not really a problem. But typically, you know, we're working with a very large n in the 10 of thousands or even more. It's actually it's a square in the security parameter. So it's using LLL in practice. I mean, in our paper, we try to do some implementation in order to show that it runs. So this is pretty bad. We cannot run LLL with really, really large things here in dimension 10,000 like that. So what we did is actually, there's something that is going on here, is that the UI are some structure. Okay, they're not here anymore. Anyway, the UI have some structure. They're a product of pi and except one and then multiply by something else. So let's try to use this structure in order to generate the alpha zt more efficiently. So, okay, the UI is here, so you know, there's this thing here, and this thing is a product of the pj divided by pi. So it's like it has a lot of structure. So the first thing to note is that if you take ui and you divide it by pj mod n, this is small. Why? Because the pj here divide this element pi star. So it means that this is of the size x0 divided by pi square, and this is of the size of pi. So it means that all of this is of size x0 divided by pi, and this is way smaller than n. So the only thing that is not a priori small is for I equal to j, so pj minus 1 times uj. Because in this time, so this is of size x0, and then if you multiply by something inverse mod n, this is like of full size. So the idea is just, okay, let's apply LLL in dimension 2 this time. I want to find a small alpha j, so that alpha j times this value here, mod n, is small. So I'm just writing down this small matrix and applying LLL. This is way faster.
Which j?
Sorry.
Which j is?
So for every j, I want to do that.
Oh, every j individually.
Yes. So I'm doing that n times. So I choose B so that LLL find a short vector here on the first row. So it's alpha j times this thing, beta j. So beta j is alpha j times this element here. And I want alpha j to be more or less of the size of square root of p, and beta j to be of the size n divided by square root of p. Okay, so I can choose B so that LLL will find a vector of this size. And then the new zero testing element is just a linear combination of this small alpha j, so times this pj minus 1, and times some additional randomness here that we add to make sure that all the attacks are more difficult. Okay, so why does it work? So I have this new zero testing parameter here. Let's keep in mind that so n is bigger than x0, so it's roughly x0, and you have the size for 1p more, so x0 times pj. And alpha j is more or less square root of pj. And beta j is n divided by square root of pj. So when we apply this thing to an encoding of m, what we get is, so this was the formula of before. So now the ui times alpha zt, so it's ui times the sum. So the ith element will be ui times this thing here, so it will be hi times beta I, and this will be small, and times the rest of the sum. So this is here, this is the element, times hi beta I, and the rest of the sum, so for j different of I, then you have alpha j, and you have this element here, times ui. But this thing here, ui over pj, I said it was really small. So it means that this thing is small and this thing is small. So everything here is small. So if mi is equal to 0, then you have something small times something small, so it will remain small, not n. And you also have a plus x0 times alpha zt, but actually with an alpha zt defined like that, the x0 times alpha zt is small too. Why? Because x0 has pj as factor. So when you multiply x0 times this, then it could cancel the pj's on each, each coefficient of the sum. So it will be a sum of small things. So it means that this is small too. So when the MR are equal to 0, then you will have a sum of small things plus a small thing, so everything will be small. And when the MI is not equal to 0, then this is big here, times something small, but this will be big. And actually the A will be big too, so plus something big times something small, but it means that everything will be big again. So once again, we can prove that the zero tests work, and we have to give several PZTs. Okay, one important caveat is that we cannot work directly mod x0 anymore. So we wanted, in CLT13, we're doing all the additions and multiplication mod x0 so that the encoding does not increase in size. Now we can do them over z, but I mean the size is increasing a lot. So why can't we reveal mod x0 anymore? Because you can actually apply the previous attack, mod v0, which is x0 times alpha zt. So alpha zt is your zero testing parameter, so it's public, and is your new modulus, so it's public too. So you can compute v0. And when you apply it to an encoding of 0, you get a sum which is over z. This is a small element, so this sum is actually over z. You get this element over z. And it means that you can take it mod v0, and it will remove the a. And we wanted to use the fact that the a had some randomness. So of course, if we reveal the x0, then you can cancel the a. So it's completely useless. So you can apply the Chéon-Al attack mod v0, and you don't want that. So you cannot make x0 public. So there's a way to solve the increasing size problem. And the idea is just at each step, so after each multiplication, you will reduce your encoding with a ladder of encoding of 0. So I give you a ladder of encoding of 0 of increasing size. So an encoding of 0 of size x0 and of size x0, 1 bit more than x0, and then 2 bit more than x0, and then 3 bit more than x0, etc., up to x0 bit more than x0. So you have a large encoding of a decreasing size. Okay, so you have this is the size of x0. So this was your first two encodings. So you multiply them, you get a long encoding there. And then you remove this one in order to decrease the size. Up until you get something which is of the same size as x0. So you just you remove them. You just look at the most significant bit and you remove it until you have a small encoding. And since it's an encoding of 0, you're not adding anything to the value. So you're not changing the value that is encoded. So this was described in DGHV 10. Okay, so now we solve the thing. So after each operation, we reduce the size, and then we get a small encoding again. Yes?
So if I only care about asymptotics, then I don't really care about the size, right? So isn't there a problem with the size of the problem is that A is no longer small.
Yes,
that's
yes. Yeah, so exactly. Then you will have a big A, and then it won't go in the.
But everything will remain sort of polynomial size, and
True.
You can still do everything. So
yes.
sort of the thing that bothers us more.
It's that the A is no longer small. Yes.
So it's not like we polynomial size, so we keep multiplying things.
It's polynomial in the number of multiplications.
Yeah.
Okay, so let's just try to run a Chéon-Al attack. So the first thing is you want to compute this encoding here, as before, but now you have to reduce its size first. So you have to do this, to add a subset sum of this thing here in order to reduce the size. So then when you, write it over z, so you have a small a here, and you have this element as before, but now you have this sum here. It sums with something that is coming from this ladder of encodings here. So these things here, when you try to apply the PZT and then write it as matrices, you will get the matrices as before, but plus some other matrices here, and minus another matrices times x0. So you're actually adding a lot of things. So when you invert, it's not really meaningful anymore. So it really comes up in the way of Chéon-Al attack, and we didn't see how to extend their attack in order to deal with that case. So we really wanted to use the randomness here, but actually, because of our construction, we also have this randomness here that is adding more thing, and that makes the attack work even less. Okay, so just to quickly finish, there is a proof of concept implementation. So in the papers, I try to give a small implementation each time for 6 level and 80 bit of security. The encodings are 66 million bits long. The public parameters is nearly fitting on a DVD. And so it takes more than 1 hour to generate the public parameters. But then when you do the multi-party key exchange, you have to work a couple of seconds before broadcasting your value. And when you have downloaded all the values of the other guys, you have to multiply them and apply the zero testing. And it takes like 20 seconds or so. This is on this computer or something like that. So just one small thing, it does not scale so bad with the number of levels. What scales bad is the setup phase. The setup phase is really increasing a lot if you take more levels. But these values here, it's increasing a little, but not that much.
So how many levels can you accommodate?
I mean, so this is as fast as a CLT 13, and in CLT 13, so in my thesis, I went up to 25 levels. So I think we can do, you know, up to 50, 60. I mean, it depends how long you want to spend in the setup phase, and you need to have a lot of RAM and stuff like that. But it's a small number of levels, but it's between 0 and 100. I think it's okay to say that it's implementable in that range. So in the implementation of GGH, they went up to about 50 levels too. So this is kind of similar in a way. Okay, just to conclude, so the CLT scheme has some interesting features, the composite order thing, and now with this fix, we assume that the graded Diffie-Hellman assumption, decisional Diffie-Hellman assumption is hard, but it seems that also now the attack does not extend to decision linear problem and subgroup membership, so maybe there is like still hope for a scheme that are based on these assumptions. If you want to attack the scheme, you have concrete targets in practice. The first set of parameters is for 52 bits of security. So if you come up with a good attack, you're likely to be able to break this parameter set. And then this is more or less the same efficiency as original CLT. And what are the open problems just for CLT 15? Because after we have a small discussion phase. The first thing is it would be really good if someone could further analyze and try to cryptanalyze this reparation. So we really designed it so that the known attack do not seem to apply anymore. So is it a good way to do things? Can we improve the efficiency? So currently the efficiency is not so good. The parameters are really, really big, but maybe there are some tricks that would allow you to gain something. And another thing, so we try to adapt the technique of before to GGH 13. So we first put it in appendix of our paper, but then we realized that there is a way to come around it, so we remove the appendix. But maybe there is a way to adapt a similar technique to GGH 13, and that would be interesting too. Okay, so thank you, and now is the time for the discussion phase.
High-level question. So the zero testing procedure here is still linear modulo n.
It's yes.
And the previous.
Well, I mean, in what?
Linear in
the R, you mean? In the.
So it's linear in the encoding, I guess. So
take a sum of two encodings, you get the sum of.
Yeah. So it's in linear modulo n in the encoding.
So not really, because this.
I mean, the procedure is just alpha zt times the encoding mod n, right? And you check whether that's short or not, right? So
yes.
So where do you see, where is the difference between like the linearity that's being used in the
So okay, the fact is in the previous attack you could write that down as a multiplication, and you could have really a multiplication of matrices, and now you have this sum here with this matrix A here that also depends on this value here.
So previous was linear in the R's and
yes.
Bilinear or trilinear.
Yeah, it was trilinear in this value here. And now you also have this, but this is not linear in array. I mean, not trilinear in these things here. So it's really comes up. I mean, this value too, actually. So it really comes up in the way. It really means that you can write it as a product of 3 matrices plus 1 matrix plus another matrix. But then you're kind of stuck because if you invert it, then you have a lot of cross products, and I don't know how to adapt the attack so that you can ignore this cross product or use them in a different way. Okay, so for the discussion phase, I guess the question is, what is the state of the art in multilinear maps? What do we want to do? Where do we want to go? So there are some 4 main things. So the attacks. So we really need more attacks in order to really understand what are the hardness assumptions we can make, and can we attack the reparation of the scheme or not. I mean, really a lot of work is needed in the attacks, but then you can also work on the assumption. So there are 2 things in the assumption. Is it what sort of assumption can you make on existing schemes, and can you base on multilinear maps on more nice assumptions such that LWG and stuff like that. And you have a part which is application. So something that would be interesting is to do something that is different from obfuscation. A lot of people work on building obfuscation, and a lot of techniques are, Killian re-randomization and stuff like that. Can we do something different than obfuscation? I mean, really different. And what can you do with a small number of levels? So I said in practice you can implement for, I don't know, up to 50, 100 levels. Can you do something interesting with that small number of levels? Or do you need a lot of levels to do obfuscation? I mean, what can you do with a small number of levels? And then you can have some tweaks in the design too. Do you want a public encoding space or not? Do you want to be able to invert the encodings or not? This is not particularly easy, but it could be useful in certain applications. So there is a paper, for example, that does forward secure key exchange, and then they need to, for the security proof, they need to be invert encoding, and that's not possible in the schemes we know. Okay, so that's the 4 main domains I think we have to work on. And so currently, so as I said at the beginning, we're entering this, I hope we're entering this new phase. So we have a really nice graph-induced thing. We have this new reparation. What can we do from now? Okay. So that's a discussion phase, so if anyone wants to discuss.
Yes. I don't want to discuss, I want to ask a question, if that's okay.
Sure.
So just wondering, so these GIs, right? So I think in the beginning in CLT, people thought that maybe the GIs, they can even be public, right?
Yes.
And then at some point, maybe it was not so good that they were public. So what are the restrictions that you have on the GIs? Can it be, so first of all, public versus private? Do they need to be big or can they be small?
Okay, so they need to be. Okay, so at first we said they were privates because it was mimicking GTH, but then we realized that we didn't have any attack that really used the fact that, I mean, if I published them, we didn't have any attack, except if you have only one value on one slot only. But I mean, you can go around that. So then it does not seem so bad to have them, and you can take them kind of small. So we took them exponential in the security parameter, but in a way you can take them smaller. You just want the product at the end. When you multiply all the encodings, you want that with overwhelming probability, the product, if all the values are random, the product is not 0. So you can take since you have a lot of values, a lot of n, then you can take them way smaller. So in the new scheme, that's the same. I don't see any way to exploit the GI or not. So exactly the same conclusion with them.
Yes. So also a question, I guess, for the room overall for this discussion. So like in Shai's talk, there's sort of the two modes, right? The private encoding mode, the public encoding mode. A lot of the attacks apply only against the public encoding modes of things, right? As far as we know.
Yeah, I mean,
Well,
the
except for
issue is,
13.
the issue when you specifically give encodings of zero, or things that are very close to encodings of zero, then as an attacker you have a lot of freedom in choosing how to get a top-level encoding of zero. You can multiply this by pretty much anything you want, or you can take one of the others and multiply. So you get a lot of freedom, and then you get the freedom to set your system of equation, this bilinear or trilinear thing, in many different ways, and you make matrices out of it, etc. If you don't explicitly give encodings of zero, and the only way to make encodings of zero is sort of to go all the way to the top level, and then subtract a couple of terms there and things, the type of since the only attacks that we have go through, you have to get me an encoding of zero at the top level to get a single equation, your hands are tied in the sense of the type of equations that you can make, and they don't behave as nicely. That's sort of the place where the current attacks distinguish between the public and the private settings.
Okay, so the question was, given all of that, what is, say, the simplest application we know? So in the public encoding setting, this is not exactly right, but usually public encoding is used for multi-party key agreement, things like that, whereas private encoding, you're talking about obfuscation, where you have extremely large, where you have very large levels and things like that. So I'm wondering, is there an application of private encoding with relatively low levels needed, or something much, say, simpler to analyze or understand? Is there anything that comes to mind?
So the only thing I can think of is witness encryption, but that still needs a high level,
Right.
although it is much simpler to construct than obfuscation.
What about with the order revealing encryption? Do key exchange with only
Right. There's not like public coding.
yeah, exactly.
What was it? The graph-based, you can do
The key agreement and the graph-based key, right? That only is private encoding.
That's the sort of one exceptional case, though, where we have key exchange without encoding to zero, right?
Right.
But you'd still need public encoding, right? In the graph-based key
Yeah,
exchange
but not
from the
of
graph-based. Say again?
Yes, but not of zeros.
Fair enough. Okay.
You don't need public encoding for the underlying.
Right. I mean, you always publish encodings of some things. Whether
Yeah.
application
I mean, it's
think
not
of,
zero,
but,
it's not public elements, but
But then another
Any
issue
other
about the
application?
public encodings is that if you want to use an assumption over multilinear maps to build something, and you want it to be a privacy type of reduction, then it's just really hard to think of how you can give a reduction without having some public encoding, or of things that are going to let you allow to get zero. For randomization. So that's where the issue.
Do you actually need public encoding to encode yourself, or can you get like some sort of semantic security type thing where or chosen plain text attack where you just like have a challenger and you ask them for encoding and they encode for you, right? I mean, it's not necessary. Isn't necessary that you have to
It's
encode.
hard to think of a good application where that would be enough, right? Because in general, the reduction is just a mental experiment, right? And it should be just getting something non-interactive. Right? And then it has to combine things it's gotten and give it to the adversary.
So you're saying you actually need to be able to generate it yourself versus having access to an oracle that generates it.
Right,
That's
because the
not
reduction
really-
needs to be...
The reduction needs to process the encodings it was given to produce public parameters or whatever.
Yeah. And in order for that processing to be meaningful enough, at least the way we currently think about it, it seems that you probably need to be able to get yourself a zero. I mean, not necessarily, though. Maybe there's some pseudo-random version of it, right, where you do some subset sum and it's not enough. There's not enough density to actually be able to get a zero. That would be kind of weird, though. I'm not sure what the assumption is.
So for key exchange, just to understand the state of affairs, right? The key exchange based on GGH13 is broken, right? In the sense of polynomial time, not in the practitioner sense, but polynomial time. And the CLT15 still stands, right? The thing that Shai talked about in the morning still stands. And then again, there is a funny way to get key exchange going through obfuscation, which also still stands. Which is a kind of a, but maybe that's the right thing to do. Who knows, right? So that's the state of affairs, right? So I mean, just looking at GGH13, there are two ways to get key exchange. One, the straightforward way, which breaks, the aesthetically simple way, which breaks. And then there is this obfuscated way which goes through obfuscation, which doesn't break.
Zero test in general, you can obfuscate the zero test parameter using, take GGH13, obfuscate the zero tester using IO based on GGH13.
So it's not so obfuscated.
And then say something about the result.
So the approach is not so obfuscated. I mean, there is a method to the madness.
So going to the last line on your slide, two multilinear maps. So what is the question there?
I mean, so we have pairings currently. Can we adapt any pairing application we have to this new setting? Because here we have, randomness, we have probabilistic encodings, and we can extract some value at the end, but can we build everything that we build based on pairings, and how does it compare? Do we gain anything from doing that? Can we use, I don't know, the composite order thing, which is different from the composite groups in pairings and stuff like that. So, I mean, there's something to look at and to compare here. So maybe...
So how much is known about that? How far have people gotten so far?
I don't know any...
Nothing that was published that I know of.
Yes.
So are pairings still presumably viable and the best way to go, and these are not at all competitive?
I think...
Efficiency-wise, they're definitely not with
Not
as of right
clear.
now,
If
right?
two linear, it's not clear at all.
But,
Not
but you still have lambda to the 3 just coming from not even the, right?
That's true.
But I mean, pairing is not magic either. I mean, you pair into ZQ and over there you have sub-exponential. I don't know if anybody who actually went carefully and tried. I guess would be my answer.
Tried what?
Try to look at applications that only need only need bilinear stuff, and see what happens when you try to implement it using these types of maps, whether you get efficiency advantages, or, I mean, it seems like at the very least things would be more parallelizable, because these are simple lattice type operations. I don't know if anybody would try it.
So I have a question about your pre-technical book for this setting. But so for CLT15, sorry?
Louder.
Oh, louder. Sorry. Okay. So for the newest, this newest iteration of CLT15, what is the current sort of bottleneck attack? Like in the sense that for CLT13, I remember there was a clear bottleneck attack. Like that was where it was because of the. Okay, I mean, you know what I'm talking about. So is there like a current clear bottleneck attack for CLT15?
Bottleneck in what sense?
In the sense that for currently optimizing the parameters.
Because of parameters. I mean, you can't make the parameters any smaller because of
this. Yeah. For example, the number of primes.
Okay, so the number of primes comes from this orthogonal lattice attack, and since we didn't modify the form of the encoding between CLT13 and CLT15, that's the same asymptotic thing. So
that did not need X0.
That does no. You can go around it. So that's actually the thing that gave us the big number of primes, and I don't really see a way to really gain a lot from that. So yeah, I think I think this attack is the most severe one. I mean, it has the most blow up in parameters. Some attacks are really like optimized as much as possible, so that like the random the brute force attack on the noise, then we cannot reduce it much further. So I mean, we're still stuck. We have like a lower bound here, so we're really stuck. For the other, I don't really know how to like tweak the parameters. So we have some. I mean, our implementation is based on some optimized variant, and we really choose the parameters so that it gives you to the 80 steps in the attack. I mean, we're really like taking all the attack that exist, extrapolated how much time they would take, and then we selected parameters according to that. So that's why if you come up with a new attack, then likely our parameter selection will be not conservative enough, and then you might be able to attack. But from known attack, I guess our estimates are not too bad.
So again, a question for the room. Pick any particular candidate map. Is it known that say if you can break it for trilinearity, then you can break it for higher levels of linearity? I mean, is there actually a formal reduction of this type known? Or is it a question anyone's considered?
I haven't talked about it.
Just in a sense, you can think about like sort of downgrading the zero test to like a lower level, right? Just given an encoding of like k minus 3 levels, right? Multiply that by the zero test, it kind of looks the same.
Can you do it though?
There's the trilinear. What do you mean? Can you
I think the question will be, what is the structure that you're assuming for the attack with only 3, for example?
I don't want to assume any structure.
No, what is the definition of an attack? An attack is given the following encodings, I can attack. Something like that, right?
Right. So given the public parameters.
So given only the public parameters.
And well, like that would be one, or given given a key agreement transcript or something like this, right?
I'm pretty sure. I mean, I'm pretty sure that's because the idea would work.
For which setting?
All of them, at least the 2 GGHs, and I'm pretty sure that also CLT. I mean, I didn't think about the latter, if it comes in the way, but short of that. You just take an encoding at level k minus 3 and multiply it into the zero test parameter,
Right.
essentially, and then use that as the new zero test parameter. And the distributions are not identical, so maybe there's some extra stuff that you need to do.
What's the status for music for NP? Does any of the status of music for NP? Does any of the candidates still give us music for NP? No interactive zero knowledge proofs for NP. Sorry?
It's a good question.
I don't know.
Actually, I don't understand.
So in the original GGH,
Can you get both sides? No interactive zero knowledge from any of them.
it's related to the question that Chai was talking about.
No, but why not? I mean, you can go through DLN and...
There's some structural. I mean, the bilinear, the pairing
So you
thing
need
has
to
some
use the fact
exact
that it's a
thing that these
deterministic
things
encoding
don't.
for
Oh, you're talking about the actual...
Can you test that the parameters are hit correctly as a verifier?
Yeah.
Right, come back then.
We did have a statistical zero test. I don't know if it works. If you give a bunch of zero tests, it amounts to doing it statistically in the sense that there does not even exist a bad encoding that passes the zero test.
If the parameters
Yeah.
will generate.
If the parameters were generated correctly, which are part of the CRS, but not, I don't know that about CLTs, the 15 that it extends.
But there are other possible ways of getting music from MP, like through trapdoor permutation, come from IO or things.
But-
and-
From IO you
but-
can anyway.
yeah, but not directly
No, but this
from.
is okay. Yeah.
So, are you saying that even from multilinear map, there's no NIZK, or just from two linear?
I'm not sure. It depends on the model, though, right? If it's common reference frame where you can trust it.
No. So two multilinear map from because of the zero thing being needed, you will not be able to do it, right?
But then
Using CDH,
you do have a if and only for the zero test.
Yes. Well, with overwhelming probability.
no, but there could exist bad encodings which are illegitimately generated for which the zero test might come out positive, right?
Well, these do exist.
These do exist, and a bad guy can come up with in the proof itself.
So it's a question if you can generate it in the CRS, these encoding, or...
No, the CRS is assumed to be honest. Even
Yes, of
with
course.
the CRS, a
Can
bad guy can come up with bad encoding which pass the zero test, even though they're not encoding the zero.
No, but I thought you suggested that the encodings are in the CRS.
Encodings are not CRS? No,
The zero encodings,
they're all fine. But the prover has to generate some encodings as part of the proof. Those may not be fine.
So is the short answer that the only way is to pass through I/O and that we don't know how to handle the malicious encoding issue? Is that the right?
So I don't know if that can be handled in an analogous way by just having a bunch of zero tests and then taking a union bound saying that...
I think so, actually, yes. But
if it can be, then it would directly give it.
No, but there's still this problem that you could have a nice encoding on zero, but then just divide it by something random.
No, but then if you do a bunch of zero tests, then there do not exist...
No, I'm saying start with a perfectly nice final encoding of zero that's going to pass the zero test because it is an actual encoding of zero.
Yeah.
But then the way in which you construct it by multiplying other things, those are fake. Right? Because I can always take something that encodes zero divided by R, where I pick R at random, and then I have R, and then encoding of zero divided by R.
Right, but then in the GUS thing, you check multiple equations, for example, right?
No, I agree. I don't know how to make this an attack. I don't know how to make this an attack, but it does mean that there's something to be done. Right?
The final... Okay, I mean, I don't remember the details, but...
So there are at least issues, I guess that's the bottom line for Hotech. Technical question, are we still time?
You actually used the CDH-based scheme. I think that was... for GUS, there was the scheme, right, that from CDH that you had with John and there, in the hidden bit model you constructed. I think that in that scheme there would not be a...
I had a question about the N. So the capital N.
Yes.
So if you're willing to use LLL, forgetting about practical efficiency altogether, then is there hope for getting it to be much smaller?
repeat the question.
For example,
Can you repeat the question, please?
can you pick the n to be way smaller than x0 if you're willing to do the LLL, like the full LLL thing? I guess you can... Well, I would need to go through all the attacks again. I don't clearly remember the answer. You cannot take it too small, and you cannot take it too large. I'm pretty sure of that. So if you take it too large, then you have orthogonal lattice attack again. So you really, you have a small range to take it. But then maybe there is some way to have something slightly better than what we had, but I mean, that's not much different because you go from an n which is of size n times the size of the prime to n plus 1 size of the prime. I mean, the n is really, really big, so it doesn't matter so much in the end. So I would say it's not really an issue.
Besides n minus 1 times the size of the prime, because n holds small elements that must go.
So you have to be bigger than that for sure. So.
I have maybe a comment. So going back to the Bonnet-Silverberg paper, at that time we showed that, we sort of had a heuristic for why algebraic geometry might not lead very naturally to multilinear maps, but it was open as to whether you could get something from elsewhere in mathematics, such as, for example, topology or something like that. And I would argue that that would be where one should be looking, is elsewhere in mathematics to get multilinear maps, exact multilinear maps. And that may be a good topic for the upcoming conference in Irvine on mathematics and cryptography, because we're not going to have a bunch of mathematicians there. So if people want to go there and think about it between now and then, and come up with questions and come up with what it is you want, because at the time of our paper, we thought you needed certain additional assumptions like Gala equivariance, which turns out you don't need at all in cryptography. And that was part of our constraints of why that would restrict where you could get multilinear maps from. And once it was understood that you didn't actually need those conditions, that kind of opens up the possibilities for where in mathematics you could find natural maps. So that may be a direction to go in, is actually try to find something better than all of this from somewhere else in mathematics, which may actually be out there. So we had the pairings that people use from the curves have been around for a long time. Mathematicians were very familiar with them, and it just took people talking to each other across fields to realize this could be useful in cryptography. And this may be a good case where that should happen again.
With that, we will break for lunch, and let's thank Shai and Tancrède again.